Тук при мен след малко ще излезе доктор Сара Сантош. Тя е директор и основател на Maths Busking, една изключително интересна английска организация, която тренира млади артисти да използват науката и математическите проблеми като вид забавление за хората на улицата. Съответно спират ви не улични музиканти или магиосници, а математици, което се оказва, че работи доста добре. И сега ще видите нейния подход и защо всъщност това работи добре. С темата съкровищата на геометрията сега при мен ще излезе доктор Сара Сантош.
Добро утро! Как си? Аз казвам Сара Santosh, and that's it. I can't do any more Bulgarian. Thank you. We are talking about what I call gems of geometry that are just my favorite bits of geometry. Actually, it's not showing there, but will show soon. Meanwhile, if you can get onto the internet, that means you can say hello to me on Facebook, on Maths Busking, which is a project I run as a company where we do mathematics as street performance. Yes, you heard right, mathematics as street entertainment. Or you can follow me on Twitter, where my name is just written backwards, because I like mirrors, okay? So the Gems of Geometry is a collection of things I like about geometry, and I thought I would share with you. Some of them you might know, some of these things already, but I'm trying to bring some demos as well. Right, so we're going to talk about perspective. Just behind it. Okay, that's cool, that's cool. Perspective. We're going to talk about curvature, so I'll show you some stuff with triangles. And symmetry, because I do like mirrors, I told you. A little bit of a game that doesn't look like it has anything to do with geometry. It's called a set game. And we'll finish off with a little bit of topology, which is all about rubber geometry. It's not what you think. Okay, so on perspective, which is here, we just need to think about spheres and circles. This is why I chose this round shape. In this picture, this is a real picture. It was painted on the floor by the artist Julian Beaver. And this guy has lots of amazing pictures online. Julian paints these amazing images, and then he's there on the top, there, looking like he's cleaning the world. But do you think this is real? He's really standing on top of the world? Yeah? So, you know how this works, right? There's from a different point of view, it doesn't look like a perfect world, more like the real world, isn't it? But the key thing here is that from one perfect viewpoint, it works perfectly. Okay, and the key idea is how do we find that? How do we find that point? So that's another example, which will come soon. Yay. And this one here is it's one of my favorites, this gold under the floor. And the whole idea is it only works from one point of view. From other points of view, it looks ugly. You might have seen that in football matches or any sports events. We have an advert on the, yes, a few heads nodding, yeah, football. You have an advert that is only seen standing up from one camera and looks rubbish from the other points of view. So, how does it work? We need to understand how perspective works, and there's mathematics behind it. But the first thing we need to know that perspective is a projection, meaning what I see is projected on the canvas or on a piece of paper. So in this case, the artist has this eye fixed so that he has always the same point of view. Some people live like that all their lives, always one point of view, but just here is useful. He's drawing this guy, so the light rays will come from him to the eye, and then he tries to draw that on that board. So that's the projection, and we look at this 2D projection of the world. The other thing we need to think about is vanishing points. And if you're not familiar with the word in English, vanishing points, when you, for example, in this picture that I'm going to show you, the floor all these lines in the floor are all supposed to be parallel because it's supposed to be a nice checked floor. But in the picture, they kind of meet, converge in the same point. Probably familiar with that. So I'm just going to highlight all those lines. And that works as well with the lines of the roof timbers. This is a bit slow. So they're all converging to a point which the artist chose to be around the head of the main character in the picture. Just a way of focusing our attention to there. It's going to take a little bit longer than I thought, but it gives you time to appreciate that. So all those lines are parallel in reality. When we draw in perspective, they converge to the same vanishing point. If you have a different direction, the other lines in a different direction will go into a different vanishing point. So there's many vanishing points, okay? Let's see how this... maybe... Okay, so there's multiple vanishing points, which is quite important, but it's a bit complicated to study the whole perspective, so we look for simpler shapes, okay? And for simple shapes, we start with cubes. Pretty simple. They have the three edges at 90 degrees from each other. In fact, there's three main directions, and I'm going to show you a picture that looks like just like this one here. And the key idea is that the cubes in that picture are all parallel to each other. That means the face, this face here is parallel to that face there, and so this edge is parallel to that edge, and so on. So these lines here converge to that vanishing point that it's off the picture, but in this board is here. So there's a vanishing point here for all the lines this way, and there's another vanishing point here, which is that one there for the edges that way, and the vanishing point for these ones down here, okay? That means that I have three lines, three main directions at 90 degrees from each other, have three vanishing points. That means that when I, as an artist, well, if I was one, if I was drawing the picture, I would be looking at it with three main directions, three light beams coming out of my eye, all at 90 degrees from each other. And where they meet my observation board, this is where I have my vanishing points. Okay, so what I'm going to ask is one of you to come on stage just to observe something on that board. Have someone, yes, you? Yes, can I have a round of applause for our volunteer? Volunteered by me. Hi, what's your name?
Venci.
Venci. So Venci, what I'm going to ask you to do is to sit in this chair and look at this drawing. You can just sit down there, and I need to hold there, okay, and you can hold the board. And I need to put your eye just here, one eye, and cover the other one. No, here, not there. Okay? So what I'm trying to prove here is that there is one unique observation point that makes that drawing look realistic, like that world. And how is it going? Right. So what you're supposed to see, and I'm really biasing this experiment, is that the cubes are supposed to pop out of the painting. So I invite you to come and see at the end. You need to be a bit closer, okay? Just one eye. And I invite you to come and see at the end, or we'll put it outside, okay? How is that working for you?
Good.
Yeah, good. Okay, do you see the cubes popping out?
Yes.
Yes? Very good. Thank you very much. Thanks for coming on stage. Can I have a round of applause for... Yeah, fantastic. Thanks. Okay. So, what are we doing with this? What we have is that we need to... Of course, we can figure out how to find this observation point, because I know where it is, but I'm... What? Okay, cool. I missed that. Someone's going to show me that. Okay. So what we're going to do is, where's the maths here? Well, we know that if we have a line like this one, yeah, between these 2 points, and if I want a triangle that has a 90-degree angle, it has to lie on a circle that has this diameter. So I just need to get this line, make a circle that has that diameter, and I know every point on that circle is going to have an angle of 90 degrees with that. So, but then I'm in 3D space, so a circle is not going to be enough. I'm going to have a whole sphere. My eye has to be positioned in a whole sphere that has this diameter. So I need a sphere popping out of this drawing. And I need another sphere for that line there, and another sphere for that line there, which means that my eye has to lie, woo, okay, my eye has to lie on the intersection of three spheres. And I will kind of show you a little video that tells you what the intersection of three spheres looks like. They were going to come soon. Maybe I can have some help from the control room there and advancing this. Okay, no. Right. Yeah. There we go.
Here's a model of the three spheres. Concentrate for a moment on the first two. Since your observation point lies on both of them, it must lie on their intersection. Now, what do you know about the intersection of spheres? That's where lemma 3 comes in. By lemma 3, they intersect in a circle. Therefore, I can throw away the first two spheres and just retain the red circle. So all I have to look for is the intersection of this red circle with the third sphere. You can see clearly that the red circle meets the third sphere in exactly 2 points. Therefore, the intersection of all three spheres is exactly these 2 points. Well, that looks as if I've got the wrong answer, because I'm trying to prove there's only 1 point. So let's suppose this is the plane of the drawing, or the blackboard, if you like. So one of these points must be in front of the drawing, while the other one will be its mirror image behind the drawing.
Okay, right, so the point here is the one in front of the drawing. Now, if you go to an art gallery and you want to appreciate a painting from the right point of view, you know what you need. 3 spheres, yeah? Take with you 3 spheres, find intersection point, observe, well, maths can do a little bit better than that, so we call it a theorem, which we're giving you a rule to work out that point by working out the height. And there's a formula there. And those x, y, and z just mean the length of these sides, okay? And that point J there is called the orthocenter. You can look it up online, and it's a special point of the triangle, okay? But just to tell you that there is a way of finding that out, and then you can do amazing paintings, like Julian Beaver. Okay, so that's what I find surprising about perspective. And then I have a little video to show you, because I want to have a look and think of what's happening in that video. Are you ready? Okay. Are you ready in the control room? Yeah? Okay. So, this is the British Library in London. You can carry on a little bit more. What's happening is moving. Can you stop? That painting is moving. What's happening? The camera is moving as well, but even if the camera is moving, the painting seems to be moving more than it does usually. Can we have the rest of the video, please? I heard some ha's. Cool. Okay. Right. This is the artist called Patrick Hughes, and he's very interested in working in perception and optical illusions, and in this case, in perspective. Okay, that's great. So, my next topic is on curvature and triangles. So I'm going to use triangles to look at curvature of surfaces. So one thing you know about triangles is that the angle sum of triangles is, if you add up all the angles, 180 degrees, very good. Always? Yeah? Okay. Can I have 2 people on stage, please? Yes, and one more, and have a round of applause to encourage them. Very good. What's your name again? Valentina. And Valentina, you pick someone because you're brave. Can you pick someone quickly to come on stage? Okay, brilliant. And then you welcome them, and I'm going to bring some stuff here. Brilliant. Now, Valentina, can you hold the sphere? And your name is? Martin, can you hold the torus, or mostly known as a donut? Can you show it to the audience? Okay, now can you show the triangles I've drawn on them? Okay, now I want to check what's the angle sum in these triangles. So on this first one, this angle looks pretty much 90 degrees, yeah? And that one, 90 degrees, so that adds up to 180 already. And that one? So 270 degrees. You're wrong. And so are your math teachers. Oh, no, joking. Okay, what about this one? We're going to need to measure that angle. So we're going to have this paper and a pen. And because we have very strong light, what I'm going to do, you don't need a protractor for this, because I can draw the angle. Okay, then can you show, cool. And then I'll just put it together next to the other one. And then the other one. And the angle is going to be, it's slightly less than 180 degrees. Surprised? No? You knew this? Yeah, fantastic. Okay, so do you, right, ladies and gentlemen, we need a round of applause for our fantastic volunteers. Thank you, and I can have the props. Yes. Okay, thank you very much. Now, the cool thing is that, so the donut, the inside of the donut gives you hyperbolic geometry, and the other one gives you spherical geometry. And for example, so we know that the angle sum is not always 180. This is an example of hyperbolic geometry, it's a horse saddle. That, in fact, the angle sum of triangles determines how the space is curved. And this other example is work of M.C. Escher, and the reason I highlighted the lines is that the straight lines in this space are either these ones or circles that meet the border, this bit here, at 90 degrees. And these are the shortest paths in this space. So this is what we're looking at, and a triangle is a triangle that is made of shortest paths, okay? So that's why it's a little bit bendy there. Okay. This has consequences, very interesting consequences. One of them is that, well, there's a connection between angles and area of the shape. In a circle, in a sphere, for example, this is how we can calculate the area of a triangle. We measure the angles, add them up, and then we know that has to be pi radians, or 180 degrees, plus 1 over some constant that is dependent on the radius of the sphere times the area. So for example, the Earth, the radius is so big that when you put it here, this is going to be very close to 0. So triangles on Earth are very close to, angle sum is going to be 180 degrees, very close to, unless you have a massive one like the one on the sphere. Okay. You can find the proof of this online. But the consequence on regular tilings is that although in the plane, there's 3 regular tilings, meaning you can tile the space. Oh, that went very fast. Okay. I don't know what happened there, but yeah, you can tile the space, the 2D space by squares, by regular hexagons, like the streets in Sofia. They have all these regular hexagons, or equilateral triangles. Now, in the spherical space, in 3D space, sorry, on the surface of the sphere, we have 5 possible tilings only, regular tilings, that are given by the 5 Platonic solids that I put here as dice. You have the tetrahedron, the cube, the octahedron, the icosahedron, that's the 20 sides, and the dodecahedron. And if you pump them up, inflate them, you get those other pictures, okay? So there's 5. Now, in the hyperbolic space, where with negative curvature, which is like the inside of the donut, you get infinitely many tessellations by regular shape. So all you need is, if this is 4 sides, so P equals 4, and notice that here I have 1, 2, 3, 4, 5 squares meeting at each vertex, then provided 1 over P plus 1 over Q is less than half, I have a hyperbolic tiling. So have fun. So this is just to give an idea about that. Okay, so next I'm talking about symmetry. because I told you I like mirrors, and I'm going to need a camera at some point. But before we do that, I wanted to look at this video. Can I have the sound off for this video? And I just wanted to appreciate what's happening there. It's a bit weird. Okay. And in some cases, the image spins around when you spin it, and in some cases, it doesn't. Why is that? It's something to do with the angles, yes. And it's something to do that some of those images are reflections, some of those images are rotations of our real images of me. So, for example, in a box of mirrors that I'm going to show you, a tetrahedron, that is a shape that has 4 equilateral triangles, can be generated by just having that one being the real one and all the others being multiplied. So I have 24 images of that. And I have another one to show you live. So if I have the camera, switching to the camera, I'm going to show you another shape on my kaleidoscope. So no surprise, I'm going to put this piece, that it's for you, so you have a triangular pyramid, but I could just as well put a flat triangle there. I'm going to put this inside a box, and we're going to see a shape. So can you guess what we're going to see? Just by looking at the box of mirrors. Very innocent. What's going to happen? Squares. I could have squares. Okay. I could have more triangles. Okay, you ready to see yet? Can we use? No. Okay. For example, with the tetrahedron that I was showing in the picture earlier, what's happening in the box of mirrors is I put one of these pieces, and then the mirrors will reflect and reflect and reflect and reflect. So one of them is a real image, the other one is a mirror image, the other one is a rotation of it, and so you have these images being repeated over and over again. So you got 24 because you have 4 faces with 6 triangles each, so in total you have 24 images. Right, yeah? Or should we do it later? We'll do it later. We should. Okay, we're going to try and put the camera on, but before I show the kaleidoscopes, I'll bring the presentation back on, yeah? And I'll show you what I have next. Have you seen 3D kaleidoscopes before? Yeah? You have a set? No? And you do? Yeah. Brilliant. Who else? Yes, the lady there? Not too many of you. Okay, so at the end you can come and see it. Okay, brilliant. So yes, we can see the dodecahedron and the icosahedron. Well, these two have the icosahedron and the dodecahedron have the same symmetry, so I can see the 2 shapes in the same set of mirrors. And in fact, there's only 3 sets because there's 3 types of, there's 3 symmetry groups for spherical shapes. Okay. My next slide. Now, the reason I talk about this is because maths and the study of symmetry can lead you to other questions. What are the 3D shapes that tile the 3D space? You can tile the 3D space by having cubes stacked on top of each other, no gaps, no overlaps, and they fill in the whole space, going on forever. Now, cubes are the only Platonic solid, the only totally regular shape that tiles the 3D space. There are others, like this one here is done by using truncated octahedra, and they're all packed together. And there's quite a few, but it's an interesting question. And we can ask the question about the shape of the universe as well. Because, for example, if we know that by astronomical observations, if we know that space turns out to have the symmetry of a dodecahedron, and they're all packed together, we know that dodecahedra don't pack the 3D space unless it's bent. So we need to know about this, okay? We need to know about these things, and this helps understanding the space. So I had another question that was, the answer is 8. What are the possible geometries for the three-dimensional space? And it's 8. Very good, you're paying attention. So for 2D space, there's 3 possible geometries, which is the flat one, the Euclidean, the one with 180-degree angle sum for triangles. There is the negative curved, the hyperbolic, and then there is a spherical that has positive curvature. For the 3D space, there's 8 types. And this links to problems that have been solved in mathematics very recently. So I want to mention the Poincaré conjecture, that it's looking at if in a sphere, I have some rope here, actually. In a sphere, where's my rope? Yes, can I have some rope, please? In a sphere, if I have a loop around the sphere, I can shrink the loop into a point. Yeah? Okay, that's cool. So that means if I pull a loop around, and if I keep pulling, it's going to shrink. I can shrink it. If it stays, it shrinks it to a point. On a donut, that doesn't happen, because I can do this, I can put a loop around there, and if I try to shrink, it doesn't contract more. So that, of course, there are other loops. If I put a loop here, it will shrink into a point, but the point is there is a loop that can't be done. And that distinguishes the 2 shapes. So the Poincaré conjecture really asks, how do I know that a space is a sphere? And he says, maybe it's if I know how loops shrink, shrink into points, and it's been recently proved for the 3 sphere, which is a sphere that lives in the 4-dimensional space, that yes, that is the characteristic that identifies a sphere. And I invite you to read about the geometrization theorem, that it's the one that says there's 8 geometries in 3D space. And Gregory Perelman, he just recently was awarded the Fields Medal for Mathematics, which is the Nobel Prize for Maths. And he put together all this, he solved the Poincaré conjecture as a consequence of the work he's done. So he's done even higher work than that. Okay. That, and I already mentioned about the shape of the universe there. My next topic to you is, well, it's not going to be so much about cubes, but it's going to be about a game called the set game. Do you know this game? Some of you know? Can you put your hand up if you know this game? Set game. No? Okay. You get addicted to it. If you're that geeky to come here, which is, I love you for that, you get addicted to set. Okay, so the set game has a few symbols. We have so cards that have 3 shapes. The shapes can be printed in 3 different colors. They can come in 3 different shadings, and they can be printed as 1, 2, or 3 shapes in the same card. For example, I remember, do you know He-Man, that cartoon? You had that? Yeah? He-Man. Not working. Okay. So you can have pills, or this oblong shape, can appear as green, other colors, 1, 2, or 3. You can have diamonds. You can have that hatched, or the wiggle, as I like to call it. They can be different numbers, different colors, okay? Just to give an idea, it can be full or empty or dashed. And the challenge is how to make a set. And the set has a particular property. This is what we need to pay attention. Is that for each property, say color, they all have to have the same color, or they all different colors. You can't have just 2 of the same color and then something else, okay? And then again for the number, for the shading, and for the shape. So for example, if I have these cards, this is a set because they're all different number, all different color, all different shading, and all different shapes. This one is also a set. So for number, they share the same number. and the other properties, they're all different, okay? But this guy here is not a set because these two share the same filling and the other one doesn't, okay? So the book says the rules of the game, and you play with 12 cards. You put 12 cards on the she-woman, okay. What is the probability? So if I put 12 cards out, the book says that it's very likely to get a set. So you put the 12 cards out, and then one of us says, set, because we saw 3 cards that make a set. What are the odds? The book says that it's 1 to 33. It says that, so it's very, very likely. But I can't find a proof. And when I look online, I find simulations, computer simulations. But I haven't found anyone that could give me a proof of how to reach this probability. It's a really hard problem. But it can be done using, well, one way of attacking the problem is building a geometrical model of this game. And just to give you an idea, do you think I can draw with a camera? No? No, okay. So what we can do is we can model, and I'm going to use the back of this drawing here, because then you'll be able to see me. What we do is, for example, I'll say I have one dimension, that is the number. Can have 1 symbol, 2 symbols, or 3 symbols. Thank you very much, okay. Then I have another dimension that says I can have diamond. Do we have a diamond on that game? No. So we can't have a diamond. Oh, yeah, we do. Then we have an oblong thing, and you have the wiggly thing, okay? And then you could have another dimension for the color, and then a 4th dimension for the shading. But just to give an idea in 2D, what we do is the possible cards are all the possible points in this space, the 4-dimensional space. So, for example, this one has there's 2 oblong shapes. And to make a set, we need to make sure they're either in a line like this, same symbol, different numbers, or in a line like this, or they're like this, everything different, or like this, everything different, okay? And then looking for these configurations, it's many other people's attempt to prove that that probability is correct. So this is actually building a geometrical space to help you solve a problem that is just a pub game, yeah? So I just wanted to leave you with that and join solving the problem if you fancy. Thank you. Okay. So I'll leave you some time to digest that, because we're going to do, what are we doing now? Slides? Can I have my slides back on? Yeah? Okay. Okay, how much do you need? 1 minute? Right. So what I'm going to do, before what I do next, can I know who can play noughts and crosses? Tic-tac-toe. Yes, I know, the above knows. You, sir? And who else? You play noughts and crosses, oh yeah? Okay, could you come on stage for me, please? Thank you. And what's your name? Stanislav. Come on stage, please. A round of applause for Stanislav. Now, I'm going to ask you to play noughts and crosses with me, and we're either going to play on a piece of paper or we're going to play... Okay, right. I'm going to improvise a bit. Can you guys see well? You got your binoculars and, yeah? Okay, right. So I'm going to do simple noughts and crosses board, yeah? And I'm going to ask you to start playing the game, just to show everyone that you know how to play the game. So you start with a cross. Oh, he's such a gentleman. Such a gentleman. Because you should go in the center, shouldn't you? I'll give you another chance. Go on. Oh, you're trying to trap me up. I'm married. I'm married. Okay. Okay. God. Ooh. Right. And boring. Thank you very much. Stay there, stay there. You said boring because you know that this game, you can't really force a win, right? But you can draw. Now, we're going to play this on a new space. Can you hold this for me? What we're going to do, we're going to play on a cylinder, where, for a cylinder, all I do is I take, it's a square, stretch it, and then glue these two ends, right? And now I'm going to play in a cylinder. So now we can play, we have new lines, right? Because now we can play across, new diagonals, and so on. But that's a little bit hard to play. So what we're going to do, hey, we can do that here. I don't do that in the street. We do one board, and then we make two ghost boards on the side, and we just have to repeat what you would do in one and the other. Does that make sense? Can you guys in the back see anything? Yeah? Okay. Right. Or you can tweet this so the guys in the back can get it, yeah? Okay. So now, can you start? You don't have to be a gentleman. Go on. Go for it. So you play in one of the boards, yeah? And now you have to repeat what you do in all the others. Okay? Now I'm going to go there. Right. Yeah, same rules, yeah? Suggestions? Yeah, sorry? Okay, top right. Top right, go on.
Okay. This is the
whole new game, isn't it?
Yes.
So, sorry, I was just saying that there's like a line there, isn't it? Like an invisible line there. Okay? Right, okay, and I'm going to play, say I'm going to play there because I want to stop you winning. Okay?
So my only choice is to play here to stop you from winning.
Okay, and you're going to win, aren't you? Because I'm going to stop you here so that you can't do this. Yeah?
Yes.
But now you win, right? Because you can put there.
Yes.
And yeah. Right. Can you win actually? Can you?
Yes.
Yeah. Cool. Thank you very much. But now don't go away because you know that it's very close. It's not exactly the same picture, but it's very close to what you get. This is draw, isn't it? But he won with a draw. Because the middle picture is a draw. And what happens on a cylinder is that a draw configuration is actually a win. You can't draw on the cylinder. Someone has to win. Surprised? Cool. Cool. Okay, so now the next thing is, what if we have other surfaces? So, because we can play on a donut, yeah? And you can play on another thing called, I need you there, yeah? You can play on another thing called a Mobius Band. Does anyone know what a Mobius Band is? Yeah? So you all know about it. So to do a Mobius Band, what you do is instead of getting your board, can you hold that for me? I'm going to need a scissors, which is somewhere here, thanks. Instead of doing this, what you do is you flip it, right? And then connect. So I'm going to give you, you're going to take a postcard that shows you, I think it's in the floor, the red thing. I'll give you a postcard where you can go away and play it. Brilliant. I think, yeah. And in that one, I'll leave to investigate. And to make the donut, you can play on that one as well. Right. So you know what happens with the Mobius Band if you cut it, if you do this? Yeah? If I cut it this way, do you know what happens?
You get two Mobius bands.
What do you get?
Two Mobius bands.
Two Mobius Bands. What do you think? We're not sure. Okay. Can you continue cutting for me?
Yes, of course.
Okay, brilliant. You can continue cutting there. Aha. And what else do I have? Well, meanwhile, I'm going to ask you, got two cylinders there. If I glue the two together and cut it, what do we get? Okay. Whoa, you nearly, right. Where's the other half?
Yes.
Where's the other half? Can you show it to them? That was a nice round of applause. I think you need another round of applause. Go on. Very good. Right, so you got a bigger loop, and then you can go and decide whether it's a straight loop or if it's a Mobius loop, okay? Now, can you hold this for me? Because what I'm going to do, the challenge is, I have 2 cylinders. Can you attest there are 2 cylinders? Yeah. Okay, and I'm going to ask you to cut through them. Okay. And puzzle for the audience. What's going to happen? What's going to happen? So I put more tape, or is that secure enough? That's secure enough. No?
Secure enough, but how do you want me to cut
Okay. So we're going to cut it. I'll start it for you. Okay, so what we're going to do is we cut half the width, like we did before with the Mobius bands, right? And even in the crossing, you need to go through. Okay? Do you see what I mean? Just continue, do that. Okay. And I take the other one. 2. Short-changed. Right. What do you think it's going to get? Not sure? What do you think? Don't know. What do you think? 2 connected rings? Okay. Are you ready for the moment of truth? Okay, now you can continue cutting the other half. Okay, it's a pair of handcuffs, isn't it? Almost. Hi. Push to get away from you, really. Okay. I think you're doing really well. I just had something else here that is gone. Right. Okay. Right. And you cut it. Okay, so can you hold it there and pretend? Pretend. Go square. Okay, let's go for the photo. Yeah. Okay, very good. Now, time is up, so I'm afraid I'm going to have to leave you to explore the rest of geometry yourselves. I'm just going to put my last slide on. Thank you very much. Another round of applause for our volunteer. I had something else prepared, but I think he went away somewhere. If I find it, I'll show you. Okay, clicker. No. Can someone advance the slides for me then, right to the very end? So, is it there? Okay, lovely. Thank you. Yeah? Okay. So, all I just what I want to say is that there's fantastic things about geometry. There's things to do with our universe. There's things to do with beautiful shapes. But I just wanted you to have a bit of fun with it. And at the end, maybe afterwards, if you like, I can show you a few more tricks of what we do in the street that can involve ropes as well. So I just want to leave the last slide on, if they help me, with our contact. And I do look forward to hearing from you. And if you're interested in doing science and mass communication, I do encourage you to do so and share the beauty of geometry and the beauty of science to everyone you meet. Thank you very much. You've been a fantastic audience. Thank you.
Ако ви